afternoon everyone, respected professors and my fellow classmates. I am Rahul and today I am presenting on the topic towards single atom tracking and imaging for quantum computing applications. I'll quickly go through the table of content. First I'll explain what is the motivation, what is the problem statement, state of the art and literature review regarding the single atom tracking and imaging, what are the preparations and current status of mind, then research gap and industry applications that we will fulfill, and then we'll conclude the session with the review. Okay, so quantum computing in a nutshell. So a quantum computer uses fundamental principles of quantum mechanics, which is superposition and entanglement. And unlike classical bits, which uses binary things, that is 0 and 1, quantum computers use the superpositions of 0 and 1. So they can be at the same state. A particular quantum system can be at the same state. So what is the advantage of that? We will get the problem solution in very fast amount of time. Say for example in factorizing or in quantum simulation and optimization. So it is compared to classical computers much faster. That's why we're using it. So the very fundamental building blocks of the quantum computers are qubits. So there are different platforms like who are like into this generating qubit. Like Google, they as a company they are investing a huge amount of qubit generation on this superconducting circuits, which uses the Josephson junction and microwave control. The other company, that is INQ, which are using trapped atoms, and they are using the charged atoms in presence of electromagnetic field to implement the qubit. The other company is PsiQuantum, which is using a photonic pattern. And the next company that I want to mention is Q-Era. This Q-Era uses a neutral atom quantum computing with the help of optical tweezers like traps. They used to use the laser beams for optical trapping applications, and then they will generate the qubits out of it, a defect-free atom. Now, since I have mentioned that neutral atom quantum computing are very scalable in terms of optical tweezer application, that's why here also we are trying to use those ideas of neutral atom quantum computing. And the fundamental, as I have explained, the fundamental building block is qubit. So the central challenge is to make the atoms behave as a qubit. And how to do that? To trap, stabilize, and image single atoms with high fidelity. So requirements for that would be a stable mod, magneto-optical trap, which will cool and prepare the atoms in an atom cloud. Then using the optical tweezers, we will isolate and trap single atoms. Then here comes the power stabilization part, which will ensure trap stability because the laser power is directly proportional to the trap stability, the depth of the trap. So if the power is fluctuating, we won't get the stable trap and atom will drift apart. Then next thing will be high sensitive imaging. So to detect the single atom presence with very high fidelity, because we have to make sure that okay, single atoms are present over there. Now moving on, what is happening in the international level, the state of the art and literature? So I would like to mention that Stephen Chu, he first demonstrated the trapping of single neutral atoms with tweezers in 1987, and for that in 1997 he got the Nobel Prize. He basically uses the idea of optical molasses, where this is a 2D laser beams are there. In 3 dimensions, when we see, it's a 6 counter-propagating beams, and at the center with the Helmholtz coil for the magnetic field, and then the atomic cloud which will accumulate at the center because of the laser beam from different directions. Now moving on to the single atom imaging. So the single shot image of 2 single atoms, which are these are separated by 10 micrometer. So you can see that it's like a single or maybe 4 or 5 pixels in a single atom. But it is done by David Pritchard in 2017 from MIT. And then these are the efficient assembly of a 324 atom array from Brouwer's group in 2016. And this is basically the optical tweezer, and these are optical tweezers in SLMs, and with the help of special light modulator they use different laser beams, and they can make the defect-free atom, and with the remaining reservoir atoms, as you can see. There is also a recent paper from Nature, which is a tweezer array with 6100 highly coherent atomic qubits, which is from Nature. It is published on 24th of September, just 2 days back, and this is from Manuel Andres group. It is from California Institute of Technology, and they are also claiming that okay, it's right now we have a control over 6100 highly coherent atomic qubits, which is very helpful for quantum computing applications. Now, what are my preparations and current status? So, first of all, because it's an optics lab, this is our lab called Atom Quantum Technology, and there are a huge number of optics, lenses, mirrors, ultra high vacuum chambers, the trap is there, different lasers are there. So first of all, I need to understand the handling of the optics and what are the safety precautions that I have to take. Then I used to get the exposure of experimental hands-on with oscilloscope, red pit cables and fiber coupling. There are lots of cables also, and how to do the fiber coupling. These are the basic things that I have done. After that, I have done photodiode characterization. So this is a voltage versus power graph. This is experimentally observed data of one of our photodiode, which is FDS100 from Thor Labs. It is a silicon photodiode having a range of 350 nanometer to 1100 nanometer, which is useful for a laser, because the laser that we are using, the diode laser, it is 980 nanometer. So I tested the linearity of photodiode response with respect to the optical power, that whether it is linear or not, so that we can detect it for the power stabilization setup. Moving on, I did the beam characterization also. This is a curve fitting with the help of Gaussian fitting in the Python program. So you can see that this is the X profile and this is the Y profile. In the X axis, actually what Python does is it makes a grid line from 0 to 100. It divides into sections, and similarly in the Y axis also, and it tries to put it in the center, and then it plots a graph. Again, in the X axis you can see the X position, and in the Y axis it's just the position. So in X axis, the blue line, the blue graph or the blue plot, you can see it's the X profile, and it is for the from here to here it will scan, and this particular plot that you're seeing is the intensity profile. Similarly in Y axis. Why I did this? Because we need a fitting of tweezer beam to check the Gaussian nature of it. Now, plan for upcoming months. So first of all, we need to do power stabilization test for tweezer beam. So because as I have mentioned earlier, the tweezer beams are very important, and the power stabilization thing is it should have to be less than 1% of RMS value, so the fluctuation will be very less. Then only we will be able to properly trap the atoms. The second thing, we will optimize the magneto-optical trap for better atom count, so that we will get the higher number of atomic clouds, and from there we will trap the tweezer beam, the single atom. The third thing that we will do is trapping of single atom through tweezer beam, and we have to align those particular tweezer beam so that it will go through the center of the atomic cloud. Then only we will have the better chance to trap the single atom. Otherwise, if laser beam, the tweezer beam is coming from this direction and atom cloud is this direction, then we won't get the single atom trap. The fourth thing is imaging calibration for proper detection. So we have SCMOS camera also, we have SPCM also, single photon counting module. So first of all, we will try to detect the signal through SPCM, and then we will try to image it with SCMOS camera. These are my plan for upcoming months. Now, what are the research gap and industry applications? So identified research gap is lack of indigenous demonstration of single atom trapping and imaging. So here in India, we don't have this particular demonstration, but in global, the scaling, as I have mentioned earlier, that there are hundreds to thousands of qubits in Europe, US and China, they have trapped. Industry applications. So it has a huge industry application like in quantum computing, quantum simulation, precision metrology. They are useful because they are scalable, they are fault tolerant architectures, and also National Quantum Mission, which was funded by Department of Science and Technology, Government of India, that is also supporting it. That conclusion. So my project goal is single atom trapping and imaging for quantum computing application. The steps that I need is power stabilization, single atom detection, high fidelity fluorescence imaging. The impact it will give is it fills a key experimental gap and contributes to global efforts in neutral atom quantum computing. So here are the few references. Thank you very much.
Okay. Good. Now you see which atom you are trapping?
CGM atom.
CGM atom. The size of atom is very small, no?
Yes.
How do you image that? How do you see that it is trapped?
Yes, sir. So for that, first of all, we will need a SPCM, which is single photon counting module. So we will have to see a signal from the atom that okay, it is trapped. So what we will do is we will place a SPCM first of all, so just to detect that whether it is there or not. So we will get a graph, we will get a plot, that the intensity plot, the fluorescence imaging that we will take. Then from SPCM we will get it. After that, we have verified that okay, in SPCM we have a signal, we have detected it. Then we can move to the SCMOS camera for the image thing.
Is it a single beam trap or multiple beam?
It's a multiple beam trap, sir. For the magneto-optical trap, we are using 6 beams, and this optical tweezer beam, it has a wavelength of 980 nanometer. So that will be a single beam.
Trapping is done by
980 nanometer.
980. How many beams?
One beam.
One beam. Yeah. And which force is responsible for trapping?
So there are two forces, which are, first is scattering force and the other one is gradient force, and they both are
in your case.
Yes, sir, both forces are gradient force is responsible. So I have one slide also. Wait, I'll explain it to you. This thing. So this is a tweezer beam. Say for example, this is a beam base, and this is our atom at picture. We want to trap. So the particular forces acting over here are scattering force from the laser line, gradient force because of the intensity distribution. As I have explained in the Gaussian profile, so there the intensity in the position, like they are different. So that particular intensity difference creates a gradient force inside. So that's why the atom will get trapped inside. So there are both forces acting, but the main thing is gradient force has to be stronger than scattering force. Then only.
I think we should also discuss the dipolar polarizability and how the trapping depth comes, and maybe in the next presentation we should.
Yes, I'll definitely.
Great.
Yeah, so when you were looking into, let's say, cesium atom, right, fluorescence, so where do you expect fluorescence? Do you look at any spectral characteristics, or you just look at in the camera itself, just its how does it emit, right?
Yes, sir. We will look, as I have mentioned, that first we will see from the SPCM that whether it is single atoms are trapped over there or not through the signal. So that won't give us the image. It just give us that, okay, a detection part of thing, kind of a graph, like histogram. We will plot that. So there's a method which we will first try to take the image as a background thing, and then we will try to take image as a when it got detected, and then we will subtract those things. So then we will get a plot that,
So
okay.
where in terms of spectra, where you are expecting, I'm just curious to know, for a cesium atom, where would be its emission, like fluorescence emission?
Fluorescence emission.
Any idea?
Sorry, sir. I don't know.
And also you mentioned that you have.
It's in the visible wavelength, but it's in
visible. So you have mentioned that so far you have not, like, done any sort of progress or whatever you proposed so far. You just look at the power diodes,
Yes.
profile. So you're gonna try with
Power. So my first aim would be to stabilize the power of the particular optical tweezer beam. So so I'm doing a literature review in which there's a circuit with the help of acousto-optic modulators, and a circuit is there with the help of the photodiode characterization that I did. So those are the things that is needed for the power stabilization, and the red PTI also that I'm mentioning, it is a FPGA algorithm based graphical user interface. So with the help of that, I can we can stabilize the power of the particular thing. So that becomes.
Okay, thank you.
Ankit.